So good morning. We will start today's lecture series of this Gyan course with my lecture on multiferroics and magnetoelectrics and what is their application in terms of IoT and the smart world. So before I start, I want to thank Professor Srinivasan for accepting this Gyan course with me, and also I am thankful for the Gyan organizers for providing me opportunity to share this course with distinguished Professor Gopalan Srinivasan. With this, I would like to start my talk today. So sustainability is a buzzword, right? And we all are worried about sustainability. So what is our contribution as a scientist and researcher towards sustainability is very important to understand. We are progressing towards a smart world. We are trying to make things smart. We are developing the technology, but there is a cost. So what is that cost? So let's see. So we have a desire of the smart world. We all know, right? We want to make everything smart. So we are looking for smart cities, smart hospitals, smart surroundings, smart working place and whatnot. See, this is what we are at right now. Everything is smart and this is what we desired. But how do we achieve that smartness? So I'll talk about a very small example, very crude example. Suppose you have some problem with your medical condition, you have high blood pressure or you have high pulse rate, but you need to be monitored and your doctor is not available 24/7 in front of you physically. But if you are wearing a device, a sensor, sir talked about yesterday, some sensor which can sense your cardiac condition, something that can sense your blood pressure and which you are wearing. So wearable electronics is the name for that thing. And then the doctor, wherever he is in the world, he can access it through internet. But for that, it has to be connected, right? Everything has to be connected to the other things. So how do we connect all these things? So everything is connected to everything. That means lots and lots of microelectronics needs to be installed. Lots and lots of sensors needs to be installed. Not only installed, but they need some energy to run, right? So this is how we do. We connect everything to everything and we create a digital nervous system where everything can communicate to everything. So your car can communicate to your home, your wearable electronic device can communicate to the hospital with your doctor and many other things, right? So this is how it works. But what are the challenges? So if you see this, about 30 billion sensor connected by 2020 already. We are in 2024 and 212 billion total number of available sensor enabled objects are there. What does it mean? 212 billion is actually 28 times the total population of the world. So the people are less, but the sensor and the microelectronic devices are more. And it means it is projected that by 2030 we will be needing 40 to 50% of the energy to run that. And we are going towards that. So what is desirable? The sustainability is the desirable thing, and we need to have responsible energy consumption, affordability and sustainability, right? So what is the solution? How to achieve that? So this is the future sensor trends for everything pretty much. And if you see, since we are focusing on magnetoelectric materials and multiferroic materials, so magnetic and electric combine together make 14% of the sensor which can be used in Internet of Things, right? So we need sensors. We can use magnetoelectric sensors, but what qualities we want in those sensors? So we actually want them to be cheaper possible. We can work around and we can get the material which is cheap. It has to be more power efficient. We can work in the scientific way and we can find out the ways to work and we can have some more power efficient sensors, and it should be easy to use. That also can be looked around. But can we make them smaller and smaller? Can we scale down them to so much? So that is the task that we need to look at. And materials and devices that we need to work for Internet of Things should be compact, low voltage, low power and low leakage. So this all needs to be achieved to sustain the world that we are progressing towards, right? So electromagnetic devices are desirable because we have seen the trend, and electric and magnetic sensors are desirable and they are useful in various applications. But we need to scale down the device. So can we scale down the device is the question. So scaling of device, Gordon Moore, who was a director of research and development and Fairchild Semiconductors, and he was also a co-founder of Intel Corporation, he published a paper where he claimed that in every year, initially he said every year, the number of transistors are doubling and on a microchip, and that's how the speed of computer is doubling every year. But it was in 65 that he claimed that, and then in 75 he revised that and he said every 2 years it will be double, the number of transistor on a microchip. This is not a law, but we call it Moore's law. It was predicted, and it comes out that it was true. It actually became valid when we looked at the years behind. So initially it was electromechanical device which used to work as a transistor. Then we had relay. See, if you notice the size and the year, then you can see how we evolve and how we have scaled down the devices. Then we came to the transistor, which we also these days see in the labs which you work with, and then it came the microchip. So you see the microchip came around 75 here, right? That's when he revised his paper, and then from then onwards it held true. So if you see the size of the transistor over time, you see the typical size is mentioned on the y-axis and the year. So by now we are at the limit of single atom. We cannot go beyond that, right? You can miniaturize a thing, but not beyond the limit of the atomic scale. So we are here. Now what is next? We need to miniaturize, we need to increase the speed, we need to store more data, we need to make things work, we need to make things connect, but what do we do for that? So what does it mean? See, 2015, the size of the transistor was 10 nanometer. In 2017, it was 7 nanometer. And then we are here. So again, what I am repeating, that what do we do, how to achieve? So at present, what do we do? At present, we use charge of electron to encode the information, right? 0 and 1. You are very well aware that binary codes and all this. Yes, yes, please, ma'am.
Is there any lower limit for scale down approach?
Yes, so beyond atomic level you cannot go, right?
Can we reach and devise a device at that atomic level?
No, the size of transistor can reach a little less than that, but I don't think device can be of that size.
Because I had read something 4 nanometer is the limit line.
Okay.
Not less than that.
Right.
Is it true?
I am not certain, sir.
Because
do you have?
I am not that much familiar with the electronics part of this.
Right. Yeah, so I think I am not certain at this point. I also need to look at it. But sir, if you have any comment, please.
So somewhere in research paper I had read it.
Okay.
4 nanometer is the limit. But they had not given the reason, valid reason for why 4 nanometer is the limit.
Okay. So we need to look into it together. Yeah. So at present we use the charge, as I said, binary numbers, you are aware. What about if we also start using the spin of the electron? So that may work out in our favor, right? So there will be another fundamental unit which can be used to code and decode the information. So what is spin? We all know every electron has a spin, and an electron can have 2 values of the spin, that we know. So electron actually behaves like a tiny magnet. So how those spins are aligned in a material, that decides the magnetic behavior of that material, right. So if they are randomly aligned, it is paramagnetic. Yesterday we talked about it, and this is the behavior of MH curve, so magnetization versus applied magnetic field, and the chi-t, susceptibility as a function of temperature. This is what you get when you have a paramagnetic material. Then ferromagnetic, when the spins are aligned parallelly, and then that is what you get, and this is what you get. So Tc is the Curie temperature. Beyond this temperature, a ferromagnetic material behaves like a paramagnetic material, and below this temperature they are ordered in parallel fashion. Similarly, antiferromagnetic materials, spins are anti-parallel, but then when you consider, so for antiferromagnetic materials, the critical temperature is named as Néel temperature. It is as good as Curie temperature, but in antiferromagnetic materials, and here the material beyond Néel temperature behaves like a paramagnetic material, right. So this is the magnetic ordering which we can use. Now electric ordering, we are aware there is a dipole, and that, so similarly electric order can also be paraelectric when the poles are not very well aligned, and that is how it is, okay. So it is analogous to material. Now the task is, can we combine a ferromagnet and ferroelectric? If we can, then can the properties be combined? You can combine two materials, but then the properties also can be combined. So if you combine a ferromagnetic with a ferroelectric, you can achieve a multiferroic material, because it has two ferroic orders, ferroelectric and ferromagnetic, in the same material, right. So electric field, now combining is not enough, you have to achieve the coupling between these two. So to achieve the coupling between ferromagnet and ferroelectric material, you need to work out with the science and with the understanding of the structure and various factors like critical temperature, how the intrinsic properties are working, and other things. So what is the rationale? Multiferroicity is achievable on paper, yes, we can achieve it, but it is difficult to achieve in a single phase material. Why it is difficult? Because see, for a material to be ferromagnet, you need partially filled d orbital, right. You need spins which can contribute to the magnetization. So partially filled d orbital you need. And for ferroelectricity to exist, you need empty or fully filled d orbitals. So this is mutually exclusive, right. In a single material, this is not achievable. So this is the problem which is very well known in the multiferroic and magnetoelectric community, that this is chemical incompatibility. Now ferroelectrics needs to be insulating for polarization to exist, and ferromagnets often are conducting materials. So it is not easy to achieve in the single material. So how to combine ferroelectricity and magnetism in one material is the task. So let us see. If it is collinear, there is no magnetic moment, right. If it is anti-parallel spins, two electrons are anti-parallelly aligned, then you cannot have. But what if they are canted? So if they are canted, you get some resultant of magnetization, right, because they are not completely cancelling each other here. So you get some magnetization. So canted spin can result in a magnetic moment, okay. Bismuth ferrite is an example which sir discussed yesterday. See, so here is the example, and iron is the contributing factor for the magnetization in bismuth ferrite. And in bismuth, so see, there are two different atoms which are contributing to magnetization and ferroelectricity. So bismuth is contributing for ferroelectricity in bismuth ferrite, and iron is contributing towards the magnetization. So bismuth has 6s2 lone pair electron which are responsible for the polarization, okay. Now bismuth ferrite, so good, we have a material bismuth ferrite, it tweaks the criteria for multiferroicity. It is at room temperature, what data is achieved, it is ferromagnet and ferroelectric. Then what is the problem? We have a material, but there is a problem. It has high leakage current, so it is not a very good ferroelectric material, right? It has weak coupling between magnetic and electric. What does it mean, weak coupling? That means if you change the electric field, you cannot control the magnetization, or if you change the magnetic field, you cannot control the polarization, right? So that is the difference, and that coupling needs to be achieved. That is the whole idea. You can have a material, you can have, but if they are not coupled, if they are not acting at the same time, and if they are not interconnected so that you can control one by another and the other by first, then there is no point. So it cannot be effectively basically used in the devices, right? So bismuth ferrite was existing, but it cannot be used. So what are the ways to achieve multiferroicity? So one thing is we find materials like bismuth ferrite by understanding the structure, and in single phase we try to achieve the multiferroicity, or we combine the two materials and then find the way around, right? So I will discuss both the cases very briefly. So we in our group we have been working in rare earth orthoferrites for the reason that rare earth ferrites give us a good opportunity for 3D 4F interaction. So see, if R FeO3, so rare earth has 4F orbitals. If you go from here lanthanide to lutetium, you get differently filled F orbital, right? And you have iron which has d orbital partially filled. So 3D in iron and 4F in lanthanide. So 3D 4F interaction gives us an opportunity for complex magnetic and electronic behavior to exist and to analyze also by understanding the dynamics of 3D 4F. So here we have worked on samarium orthoferrite SmFeO3. We pick up samarium and we investigated it, and finally we found out that there is a twist in polarization. I have named it a little to make it interesting. There is no twist, we just found out that if there was exchange in striction, so there is magnetic interaction between D and F block elements and they induce the polarization. So they have induced the polarization in samarium orthoferrite, and we further investigated. This is the structure. It is distorted perovskite. It is orthorhombic. Space group is PNMA, or it is also represented with PBNM, and these are the lattice parameters. So we have looked for canted antiferromagnet whether it is existing or not. We have looked for exchange interaction, we actually found out it does exist, and D and F orbital interactions was seen. So we could say that there is a possibility of multiferroicity. So we synthesize it at nanoscale using sol-gel method, and we prepared nanoparticles which were under 100 nanometer size, and it was confirmed about 65 nanometer average size, and we confirmed the elemental existence. Samarium, iron and oxygen were in the proportion, so it was confirmed. Then we saw that there is a transition at 480, as you see this here, 480 degree. 480 degree Kelvin, there is a transition which is a spin reorientation transition. So spins are reorienting at that transition to understand it. Then we also saw that permittivity has some changes at 480. So that means this is magnetic behavior here, where spin reorientation is taking place at 480, and similarly here you see there is a sharp transition for the permittivity in terms of temperature at exactly same temperature 480. That means simultaneous ferromagnetic and ferroelectric behavior is observed near room temperature, right? So now we try to find out, is there a link between these with the structure? Is structure playing a role? So structure is a crucial thing to decide the properties of any material, physical properties. So we looked into the link through atomic vibration. So we were looking for spin phonon coupling. You must have read a lot of times what is spin phonon coupling, right? So phonons are nothing but they are discrete unit of crystal vibration. So this is how, if a crystal is existing and these kind of vibration, this is phonon. This is the effect of phonon on crystal, and that's with phonon you can measure the vibration in the crystal. I am saying it very crudely. So Raman effect is a way to measure the spin phonon coupling. So what happens, if incident light is put on a sample and it reflects the same wavelength, it is Rayleigh scattering, right? But if the wavelength is less, then it is Stokes-Raman scattering, and if wavelength is wavelength is short, then it is anti-Stokes, and if wavelength is longer, it is Stokes. So this technique, Raman's technique, we used, and this also tells us that incident light induces molecular vibration. So Raman's technique is based on this fact that incident light induces molecular vibration, and then wavelength of scattered light changes. It will be either Stokes or anti-Stokes, and then it is a Raman scattering. So see, if these are the magnetic spins, right, here, and if there is effect of phonons, if there is incident light, then this is spin phonon coupling effect. So vibration of the atom also contribute in the spin, and that's what gives you spin phonon coupling. And how do we measure? We measure it with Raman spectra. This is just a animation to make you understand how it affects, how the spins are affected when the phonon is existing and spin and phonon are coupling. So we do Raman spectra, and then we take data from this spectra and plot it in terms of Raman shift. So see, this is Raman shift of 150 to 246, and then here we have plotted this, and you see again at 480 degree there is anomaly, right? That means spin phonon coupling is taking place. So it kind of confirmed that structure is playing a role at 480 degree, where we are getting the connection between ferroelectricity and ferromagnetism. So finally we could conclude that there is a possibility of multiferroicity in samarium orthoferrite at 480 degree Kelvin, and spin and phonon coupling are contributing in that effect. Another example of rare earth ferrite which we studied is lutetium ferrite, where again I was intrigued with the 3D 4F dynamics of rare earth ferrite, and we worked, and it was very interesting. We tried to synthesize nanomaterials, and we thought we will do the different morphology of the two materials. So we prepared nanoparticles, we also prepared nanofibers. Now nanofibers are drawn, so there is strain associated with the forming of the nanofibers, right? And nanoparticles, as you know, they are quantum confined materials, so there is already property change in comparison to bulk. So we wanted to see how, as compared to bulk, the properties will change, whether it is nanoparticle and nanofiber, and is there any difference in nanoparticle and nanofiber. So we synthesized. Then we were trying to find out what structure it is. The structure supposed to be orthorhombic, but it was not orthorhombic. We were investigating and we were seeing there are few extra peaks, and we were not able to find out what it is. And I was telling my colleague all the time that we need to resynthesize, it is not pure, we need to resynthesize, it is not pure, and we did 10 times, and every time we got the same result. Later one day we were sitting and matching the peaks, and then we thought, why don't we match it with the hexagonal part of hexagonal lutetium orthoferrite, and we did, and everything was matched. So, there was a combination of orthorhombic and hexagonal in the same material. So, we got more interested, okay, we should investigate this instead, and we realized when we do the Rietveld analysis of the X-ray diffraction data, the structural data, what we found was in nanoparticle, you see nanoparticle we got 73% of orthorhombic and 27% of hexagonal, and in nanofiber it is exactly opposite, while they were synthesized at the same temperature. So, we tried to understand, and we concluded that it is the strain which is associated in synthesis of nanofiber is contributing, and that is why it is favoring the hexagonal phase in the nanofibers. So, hexagonal is dominant in nanofiber. Now, we also investigated Raman, and we found that in both the cases orthorhombic and hexagonal both are existing. Now, next we tried to see what is the distortion in octahedra. So, using Rietveld analysis, we also checked the bond lengths here, you know. So, it is a powerful tool, X-ray diffraction is a powerful tool, you can do so much with that. So, we tried to see what is the distortion in terms of orthorhombic and hexagonal, and we did find that there is considerable distortion which may contribute in the physical properties, because the structure is a very much driven thing by the bond lengths and other things, and the physical properties are related to the structure. So, we did TEM. We realized that the sizes and everything is under the range which can be called nano, and then we also found out with the high resolution TEM that and diffraction pattern that both the phases are existing in the material. So, it was very well confirmed. Then we observed the magnetic behavior, and you should see it is the same material, lutetium, iron, oxygen, but you have different magnetic behavior for the nanoparticles and for the nanofibers. Further, we did Xane's experiment at the synchrotron, where you can probe the local environment. So, Xane's is nothing but it measures the fine structure of X-ray absorption near an absorption edge, and this region is typically 10 electron volt to 20 electron volt. So, in that range you can probe the material and you can take the edges. So, for example, if you want to measure the iron L edge, so you can L1, L2, L3 edges, you can decide which edge may be contributing, and you can probe it between 10 electron volt and 20 electron volt, and you get the information about the local structure. So, we could calculate eventually using this experiment the crystal field splitting at different temperature of the material. So, if you see, the green one is nanoparticle and this is nanofiber. So, crystal field splitting is less in case of nanofiber, and here it is more in terms of nanoparticle. This is what we calculated, and this also contributed in understanding the unusual behavior of magnetization. We again further checked the polarization, and then we found out that they are showing some polarization, but for nanofiber it is more impressive than nanoparticle. So, nanofibers were superior in terms of polarization. So, we tried to look into the nanogenerator, triboelectric nanogenerator application, and impact force of 21 Newton and frequency of 10 Hertz we used to create the impact, and we realized that 3.4 volt we can generate for nanoparticles, and we could generate 6.7 volt for nanofibers, right. And the maximum value of current density for nanofibers is 15.9 microampere per centimeter cube, and for nanoparticle it was 0.38 milliwatt centimeter per centimeter cube, it was the power density. So, we found out that just by the structure in case of samarium orthoferrite and just by the understanding the morphology, change in morphology gave us understanding that morphology also plays a crucial role in deciding the properties. It was very evident in including the magnetic behavior and also the application as a triboelectric nanogenerator. Then very briefly I will go with a composite which we created. We created HFO, which is holmium orthoferrite, and BTO composite. We did the same thing, but we made the nanofibers which were heterostructure. So, we had one layer of HFO, over that one layer of BTO, then HFO, then BTO. So, this way we created a heterostructure which was not very uniform. So, HFO and BTO thicknesses were different. So, it was a heterostructure that was created, and then we investigated with the parent compounds HFO and BTO and we compared. So, you see the magnetism of heterostructure is actually intermediate between the parent constituent. HFO is highly magnetic material while BTO is not. So, in the heterostructure we could get something intermediate which was expected. Similarly, we could get the polarization, and then further we checked other parameters which were well in consent, and then you see we calculated the power here, voltage generated. So, HFO is generating up to 2.5 volt, BTO is generating, but when you combine them the performance is enhanced, right. And similarly, the power density is also more than double of the any of the parent compound. So, we have with whatever work we have done, we have seen the nano-composite, we have seen the single phase materials, but ferroelectricity was the achievable thing. So, these are the some conclusions, and with that this is what I wanted to share. If you have any questions, I am here to take them. Anything at all? If not, then I want to thank all my mentors, colleagues and co-workers who have been constantly supporting me. Okay, thank you for your attention and time.